Hello and welcome to this video. So in this video what we are going to talk about is what is the nature of the interatomic forces, the forces that act between the atoms within the material. So why is it important? Because we know that if you take a given material like a piece of plastic, for example, or a piece of concrete or a piece of any materials, we know that this material stays together. It's a cohesive materials. And what it means is that the atoms that the material is made of, any material is made of atoms. If the material is cohesive, it means that those atoms within the materials are attracted to each other. They are bonded to each other. And they don't want to be separated to each other. If you want to separate some atoms from each other within the material, then it means that you have to take a material, you have to apply a big force on this material to break this material into two pieces. Once you break a material into two pieces, then you have separated some atoms that used to be attached to each other, and now they are separated from each other. So in that case, if you want to simulate the behavior of materials, for example, if you want to simulate the resistance of fracture of a given materials or the elasticity of a given material, then you need to be able to predict how the atoms within the material interact with each other. How much force do they apply on each other? How bonded are they to each other? So if we want to be able to predict this, if we want to be able to predict the mechanical behaviors of materials, then we need to be able to understand and predict the action that atoms are applying on each other, the forces that atoms are applying on each other. And if we know the nature of the forces that atoms are applying on each other, then we will be able to use this within simulations to predict how materials break or how materials are compressed or how materials react under load. So if you consider a given material like a beam, for example, or any material, if you zoom in on this material, and if you zoom up to a very high resolution, at some point you will be able to see the atoms that this material is made of. And again, every material is made of atoms. And what will dictate the properties of this material is the interaction between the atoms to each other. So if you zoom on these atoms, and if you look at a scale, at a nanometric scale, at the scale of a fraction of a nanometer, what you will see within those atoms, within those materials, are some atoms that are interacting with each other. So now the question is, what is the interaction between those atoms and how does it dictate the properties of these materials? So if you have an ensemble of atoms like this, so let's consider that you have an ensemble of n atoms. Those are the n atoms within the material, and those n atoms are interacting with each other. Then the first question is, what is the energy of these systems of atoms? So what is the total energy of the system of n atoms? And this total energy, usually we would call it the Hamiltonian. So the Hamiltonian is the total energy of this system of atoms. And so we typically write it H. So when you consider the energy of a system of atoms, just like any materials or any system, there is going to be two contributions to the energy. First, you have the kinetic energy, which is associated to the motion of the atoms. And you have a second term, which is the potential energy. The potential energy, meaning that each atoms are applying some forces on each other, and this forces is going to be associated to an underlying potential energy. So this is the same kinetic energy and potential energy that you have in any kind of dynamical problem. Like for example, if you have a roller coaster like this, and if you have a ball on an inclined plane like this, so this ball, if it starts moving, it will develop some kinetic energy due to its motion, due to its velocity. And on the other hand, if it's at a given altitude, then it has a potential energy. So in this case, it's the same idea here for atoms. The material is made of atoms, and the atoms themselves will have both some kinetic energy and some potential energy. So if you think first about the kinetic energy, so the kinetic energy, of the atoms, the kinetic energy of the system of n atoms, is simply going to be the sum of the kinetic energy of all the atoms. So if you have n atoms, if you want the total kinetic energy of this system of atoms, you simply need to take the sum for I going from I1 to n of all the atoms that this system is made of. And after that, the kinetic energy of one atom is the same formula as the traditional kinetic energy of a ball or of any kind of object. It's 1/2 times the mass of these atoms times its velocity to the square. So in that case, that's the first thing. The kinetic energy of a system of atoms is just the sum of the kinetic energy of those atoms. Sometimes we don't use the velocity to express the kinetic energy. We use the momentum. So the momentum of an atom, we write it pi, and the momentum is the product of the mass times the velocity. So another way to write this kinetic energy in this case is to take the sum over all the atoms of the momentum of the atoms to the square divided by mi, and to take 1/2 of this. And so that's an alternative definitions for an alternative expression for the kinetic energy of an ensemble of n atoms. So now the second term here is going to be related to the potential energy of the atoms. So it's in the same way that if you have two masses that are attached to each other with a spring. So when you have a spring, if you elongate this spring, then you will get some potential energy that develops. So it's the same idea for atoms. Depending on the distance between the atoms, then they will potentially develop some potential energy. If two atoms are too close to each other, or if some atoms are too far from each other, if they are not at an optimal distance from each other, then they will develop some potential energy. So that's going to be the second contribution here to the system, is that the atoms, by interacting with each other, they will develop some potential energy. And so in this case, this potential energy, we don't have necessarily a uniform expression that will always work for all the systems, because depending on the types of material that you are considering, whether it's an organic, an inorganic material, or metallic materials, or an ionic material. So different types, different family of materials will have different expressions for the potential energy that develops between the atoms. So what we are going to do later is to review for different types of materials, different families of materials, what is the formula, what is a typical formula that we can use to describe the potential energy between atoms as a function of their distance, or potentially also as a function of their angles. So one important thing to realize is that the first term, which is the kinetic energy, so for example, we can write it capital K like this. This kinetic energy, if you look at its expression, it only depends on the velocity of the atoms. So it's only a function of the velocity of the atoms. So only their speed or their momentum. On the other hand, the second term, which is the potential energy, which sometimes is written, for example, as either the potential energy like this, or sometimes as U. And in this case, these terms will only depend on not the velocity of the atoms, but only on their position. So in this case, this term will only depend on the positions R of the atoms. So for example, if you have two atoms like this, their potential energy will depend on the distance with respect to each other. If you have three atoms like this, potentially the potential energy can also depend on their angle, potentially. But in any cases, the potential energy will only depend on the position of the atoms, where the position is defined by a vector that starts from the origin and that points towards the atom. So for each atom, you have a given vector position. And in that case, the potential energy does not depend on how fast the atoms are moving. It just depends on where they are. So at a given time, depending on the position of the atoms, they will be associated with a given potential energy. So the potential energy only depends on the position, while the kinetic energy only depends on the velocity of the atoms. So for example, let's consider a system of 3 atoms. So let's assume that you have atom 1, atom 2, and atom 3. So those atoms are going to be interacting with each other, and whenever atoms interact with each other, then they have an energy of interaction, a potential energy of interaction. So in this case, the first types of interaction that you will have are the radial interaction. So the radial interaction are the interaction that are between two body, so two atoms, for example, and in that case, those two body interactions, they will depend on the distance between the atoms. So for example, between atom 1 and atom 2, you will have a two-body interaction between atom 1 and atom 2, and this interaction will depend on the distance between atom 1 and atom 2. Same thing, you will have an energy of interaction between atom 1 and atom 3, so that's going to be another two-body interaction, but this time between atom 1 and atom 3, and this one will depend on the distance between atom 1 and atom 3. So this R13, this is what I call the distance between atom 1 and atom 3, and R12, this is the distance between atom 1 and atom 2. And finally, you have another two-body interaction between the body number 2, the atoms number 2, and the atoms number 3, which again is going to depend only on the distance between atom 2 and atom 3. So those are the two-body interaction. It depends on the distance between the atoms. So it's just like a spring. Again, if you have a spring like this, depending on the distance between the two nodes of the spring, the two masses, if you increase the distance between the two masses, or if you decrease the distance of the two masses, then you will have a given energy. So it's a similar behavior here. Then you have a second potential behavior. So it depends on, for all materials, you always have some two-body interaction between the atoms, but sometimes for certain types of metals, you also have some three-body interactions. And in that case, those are some interaction that depends not on the distance, but on the angles between the atoms. So it depends in this case on the angles. So for example, if you take atom 2, atom 1, and atom 3, so those atom 2, 1, and 3, they are forming an angle here. So this angle, typically you can write it 2, 1, 3, where 1 is the central atoms and 2 and 3 are the two neighbors. So in this case, because of this angle can also be associated with a given potential energy. So for example, if you take, let's assume that you take a silicon atom. So if you take, for example, some silicon atoms within a silicon diamond. So silicon atoms, they are fourfold coordinated. So they are surrounded by, each silicon atom is going to be surrounded by 4 other silicon. And in that case, it means that those silicon neighbors, they are forming a tetrahedron. So they are forming a tetrahedron that comes from the fact that they have 4 silicon atoms surrounding them. And those 4 silicon atoms, they are as far as possible from each other. And this figure is forming a tetrahedron. And so in this case, it means that the angle between one silicon and 2 of these neighbors has to be 109 degrees, which is the angles between the center of the tetrahedron and 2 of its summit. So in this case, it means that if the angle between 3 silicon is not 109 degrees, then that will cost you some potential energy. If you deform this structure, then this structure is going to be associated with some energy penalty. So that will increase the potential energy. So in this case, it means that the energy does not only depend on the distance between the atoms, it does depend on the distance between the atoms, but it also depends on the angles. If the angles do not have their optimal values, then that will cost you some potential energy. So that's the second type of potential energy. Those are the free body interaction that depends on the angles between the atoms. So in this video, we will be mostly focusing first on the two-body interaction. So the interaction that depends between pairs of atoms that depends on their distance, their relative distance from each other. So to describe the interatomic energy, so the energy between a pair of atoms, what we need to do is to do a plot. So to plot the energy, the two-body energy between the pairs of atoms, and if it's a two-body energy, it will only depend on their distance. So if you have two atoms, so atom 1 and atom 2, and you take their center, you look at what is the distance r between those two atoms, and you plot the energy associated to this pair of atoms, the potential energy of this pair of atoms, as a function of their distance. Remember that the potential energy, a two-body potential energy, it's defined for the two atoms together. That's defined for the pairs of atoms. It's not defined for one atom in particular. It's defined for the pairs of atoms. This pair of atoms is interacting with each other, so it has a potential energy. So in this case, the one very first example, maybe the first example of the most simple potential energy that you can think of, is the potential energy for a system of hard sphere. So what do we mean by hard spheres? Those are if the atoms are perfectly hard, so they cannot overlap with each other. If they become too close to each other, they cannot overlap. They will just either bounce on top of each other, or they cannot overlap with each other. But if they are not touching each other, they will not interact with each other. They will not see each other unless they collide with each other. So in this case, if we plot this energy, what does it mean? So let's assume that those two atoms have a radius that we are going to call, so let's assume that they have a diameter that we are going to call sigma. So I'm going to take their diameter. Let's assume that they have the same diameter sigma. So then we say that if those atoms in this model, in the case of hard spheres, those atoms, if they are far away, they don't see each other. So in that case, if they don't see each other, there is no potential energy. So their potential energy is going to be 0 if the atoms are far away from each other. So now the question is, if those are hard sphere materials, then those atoms cannot overlap. It means that if they were to overlap, that would cost you some energy. And if in this case they cannot overlap, it means that that would cost you an infinite energy. There is going to be an infinite energy cost to have those two atoms overlap with each other. So that if it costs you an infinite energy, then it means that they cannot overlap because there would not be enough energy to make them overlap. So in this case, the condition for those two atoms to overlap or to be at contact is that those two atoms are perfectly touching each other like this, which means that in that case, the distance between them, if they are at contact, the distance between them is going to be exactly equal to the diameter. So in this case, it means that if the distance becomes equal to the diameter, then the two atoms are now at contact and they cannot overlap with each other. So it means that now the energy would increase to infinity. It means that you cannot possibly decrease the distance between the atoms less than sigma, because that would cost you an infinite amount of energy, because those atoms in this case are perfectly hard. So in this case, this hard sphere model, it's not a very realistic model, because atoms First, even if they are not touching each other, they will still interact with each other. So the energy is not exactly zero, even if the atoms are not touching each other. And the second thing is that atoms are not perfectly hard. They can still partially overlap with each other if you force them to. So this is a very simplified model, but nevertheless, this model can work well to describe gases, where in gases, the atoms are moving so fast that whenever they are not close to each other, they will very weakly interact with each other. But at some point, if they collide with each other, then they will collide when the distance between them becomes lower than their diameter. And in that case, they will collide and they will quickly bounce back. So this types of hard sphere model is typically not a very good model for most materials, but it will work well to describe mostly gases. One potential refinement of this hard sphere model is the soft sphere model, which is a slightly refined model. So in this case, again, the idea is that you have two atoms. They still have a diameter sigma, and so they are still interacting with each other. And in this case, what we are going to do, in addition to what we said for the hard sphere model, now when we plot the energy as a function of the distance between those two atoms, as a function of the distance between the center. So in the case of the hard sphere model, this is what we had. So the energy was increasing to infinity as soon as the distance between the atoms becomes equal to the diameter. So this is assuming that the atoms are perfectly hard. They cannot overlap with each other. So now, if we want to make this model a little bit more realistic, then we need to think about what happens when two atoms starts to get very close to each other. So if you have two atoms like this, and they actually starts to overlap with each other. So now you have those two atoms, and their distance here is lower than their diameter. So it starts to overlap with each other. So in the case of the hard sphere model, that would cost you an infinite amount of energy because they cannot overlap with each other. They are perfectly hard. But in this case, what we are going to assume is that those atoms have a little bit of softness, so they can overlap with each other if you force them to. So if you provide enough energy. So the question is why atoms do not want to overlap with each other. And the answer to that is that if you look at what atoms are made of, so they are made of some protons and some neutrons, and those protons are surrounded by some electrons, and those electrons are forming an electronic cloud around the neutrons and protons. And so if you have two atoms that are getting close to each other, then you start to see the electronic clouds of those two atoms that would start to overlap with each other. And so those electrons, they are negatively charged. So the electrons are negatively charged, and the protons within the nucleus are positively charged. So those electrons that are both negatively charged, they tend to repulse each other. You cannot have two electrons at the same position because they are both negative, so they repulse each other. And also at a more quantum level, you have the Pauli exclusion principle that tells you that you cannot have two electronic clouds that are at the same position within the same quantum states. So in this case, it means that if you are forcing those atoms to become very close to each other, they will need to occupy a higher energy quantum state in order to be at the same position without being at the same quantum state. So in this case, it means that if you are forcing to have those two atoms overlap, they will start to deform the electronic clouds around them. So they will maybe look like something like this, where the electronic clouds starts to be deformed to avoid being overlapped. And this deformation of the electronic cloud is going to come with an energy cost. So in the case of the hard sphere model, we assume that this cost is infinite, so that it's actually not possible to make those atoms overlap. But in the case maybe of the soft sphere model, which is a slightly more realistic model, we're going to assume that this, when you force the atoms to become close to each other, it's going to cost you some energy, but an energy that is not infinite. So if we plot it, it means that in the case of the soft sphere model, so the energy would still be zero as long as the atoms are further away than their diameter because they don't see each other. And if you force them to overlap with each other, then that will cost you some energy. So the energy would increase quickly, but not infinitely. So in the case of the hard sphere model, that would be an infinite increase. But in the case of the soft sphere model, the energy increase, but not infinitely. So you have a finite energy cost. So this, in this case, this would be a repulsive energy. That's an energy that is positive. So that's a positive energy means that it's a penalty. It's a penalty. It means that it's costing you some energy if you want to force those two atoms to overlap with each other. You have to provide this energy yourself to the atoms. And in this case, so this is going to be an energy that will increase very fast towards infinity, but will not increase immediately to infinity. So in that case, that's a pretty, if you want to put a formula for this repulsive energy terms, that's something that is pretty difficult because it's a quantum effect. So it's related to the overlap between the electronic clouds. But one function that has been shown to model this energy pretty well is that this model can be written as it can be proportional to a ratio of sigma divided by r to, for example, the power 12. So in this case, it's a function that is proportional to 1 over r12. So it's a function that is increasing to infinity when the distance r becomes very small. And that's a function that is to the power 12. So it's going to be a function that increases very fast to infinity when r becomes close to 0. So in this case, that's the typical model that we can use to model the repulsion between the atoms that are forced to overlap with each other. We can very often model it by a function that is proportional to 1 over r12. So this is an empirical model. In this case, the value 12 here doesn't have a very strong meaning. It doesn't have any clear physical meaning, but it's just a function that is very often describing pretty well the repulsion between atoms that are forced to interact with each other. So far what we have seen are repulsive energy that are positive, energy that are some penalty energy when you force atoms to overlap and they repulse each other. So we know on the other hand that when you have a given materials, the atoms like to be attached to each other. They don't want to be separated from each other. It's actually difficult to break a material to separate the atoms from each other. So it means that there also must be some attractive energy, some attractive interatomic energy. So in this case, it means that when you have, again, a pair of atoms as a function of their distance, there is going to be, when you plot the energy as a function of their distance, necessarily, if those atoms are attracted to each other, then there has to be an energy that is now attractive, an energy that is negative. So now this energy is going to be negative. It means that it's an energy of cohesion. It means it's an energy that the atoms gain by being close to each other. And in this case, so this energy is going to be associated to the cohesion. So this energy is going to be the energy that is governing the cohesion of the atoms, the cohesion of the materials, the attractive energy between the atoms. That's the energy that makes the atoms like to be attached to each other within a given materials. So there is various potential origin for those for this attractive energy, but so here what we're going to focus on is first the energy when those two atoms have a charge. If you have like a cation or an anion, so if those two atoms have a charge, then they can interact with a Coulombic energy. So this is if the atoms have a charge. If they have a charge, then charges will either attract or repulse each other. But there is another types of forces, another types of energy that is going to be always active between atoms, even if they don't have a charge, which is the van der Waals energy. So the van der Waals energy is an energy that you will always get between atoms, even if they don't have a charge. So in this case, even with no charge, you will have a van der Waals interaction between atoms, between the pairs of atoms. So the first types of attractive energy, so this is the Coulombic energy. And in that case, the Coulombic energy is the typical energy between two charges. So if you have two ions, so that is to say two atoms that do have a charge, so you have atom ion 1 and ion 2, and they have a charge Q1 and Q2. Then depending on their distance between their center, then you will have this Coulombic interaction energy that depends on their distance. And in that case, the expression of the Coulombic energy is 1 over 4 pi epsilon naught, where epsilon naught is the dielectric permittivity of void, and the Coulombic energy is proportional to the product between the charge of the two ions. So in the same way that the gravitational energy is proportional to the product of the mass between two bodies, the Coulombic energy is proportional to the product of the charges, and it's inversely proportional to the distance. So if you look at the Coulombic energy, so for example, if I plot the Coulombic energy between one cation which has a positive charge and one anion that has a negative charge, then it means that this this Coulombic potential energy will be negative, since you are multiplying a positive charge by a negative charge, so you get a negative Coulombic energy. That means that you will have an attraction between the positive and the negative charge. And in this case, this energy behave as 1 over r, so it's proportional to 1 over r. So it's a function that goes towards 0 at very large distance. It goes towards minus infinity at very small distance. But as compared to the function 1 over r12 that we previously described, this function decreased towards 0 much more slowly than the function 1 over r12. The function 1 over r goes towards 0 very slowly as r increases. So the Coulombic interaction between the atoms is going to be pretty long range. Even if the atoms are pretty far away from each other, they will still interact with each other with this Coulombic energy, because it's a function that decreases as 1 over r, which means that it decreases pretty slowly. So now the second types of attractive energy, which will always be observed for pairs of atoms, is the van der Waals energy. And in that case, the van der Waals energy is active even for atoms that do not have a charge. So if you have a neutral atoms, so a neutral atoms means that it's an atom that has exactly as many protons as it has electrons around them. And in that case, it means that it's a neutral atom. There is no charge. So if there is no charge, there is no Coulombic interactions. That being said, so if you look at those electrons, they are forming an electronic cloud. But if you look at a given times, those electrons are going to be localized somewhere at a given position. So if you look at a given time, at a given instantaneous time, those electrons are not homogeneously distributed around the central nucleus. So if you look at a given instantaneous time, so if you take a picture of these atoms, if you were able to predict a picture of this atom, so then what you would find is that this atom, so it's made of this positively charged nucleus, but when you look at a given times, maybe you will find one electron here, another electron here, and maybe another electron here, and let's say another electron here. So if you look at now the average position of the positive forces, so if you look at the centroid of the positive forces, so now you will have in this case the nucleus of this atom is here. So in that case, if you take the centroid of the positive forces, that's going to be a point P that is centered around the nucleus. But if you look now at the center of the negative charges, if the electrons were homogeneously distributed throughout around the nucleus, then the centroid of the negative charge would be also at the center of the atoms at the point P. But because at a given times the electrons will always be a little bit on the left, a little bit on the right, or a little bit on the top or bottom, at a given time the centroid of the negative charge will not be exactly at the center of these atoms. So it means that you will have a centroid for the positive charge and a centroid for the negative charge, which are not overlapping. On average, they are overlapping, but at a given times, they are not. So in this case, whenever you have a situation like this, where you have Q, a charge Q that is positive, that is combined with a minus Q negative charge. Now, if those two charges are not at the same position, which is the case here, you have, in that case, those 4 electrons and their average centroid position is not the same as the average centroid position of the 4 positive charges. This is defining what we call a dipole. A dipole is when you have 2 charges, minus Q and plus Q at a position N and at a position P. In that case, so this defines a dipole. The dipole is a vector, so it's a vector P, and the dipole is defined as the product of the charge Q times the vector NP. So the vector that goes from the point N, the centroid of the negative charge, to the point P, which is the centroid of the positive charge. So if you take a given atom, again, at a given time, you will have a small dipole because of the fact that the electrons are not going to be homogeneously distributed. So this will define a small dipole that goes from the centroid of the negative charge and goes, the vector is pointing towards the centroid of the positive charge, which is in this case in the middle of the atoms. So it means that at a given time, you have a small dipole. So on average, this dipole would be 0 because on average, the electrons will be homogeneously distributed around the core of this atom. So on average, the point N will be located at the center of this atom. So it will be overlapping with P. And if N is at the same position as P, then the dipole would be 0. But at a given time, if you take a picture, then the electrons will not be homogeneously distributed. So there will be the center of the negative charge that will not be overlapping with the center of the positive charge. So it means that in this case, you will have an instantaneous dipole that is observed within atoms. And now, so it means that if you have an instantaneous dipole, so it means that your atoms is not exactly it's a neutral object. It has exactly the same number as positive charge and negative charge, but it's behaving as a small dipole. So it's behaving like this, where you have a small dipole where the negative charge is not on average at the same position as the positive charge. So it means that you have something like this where within your atoms, the electrons are more concentrated in one area that creates an excess of negative charge at a given point N, which is not the same as the point P that corresponds to the positive charge. So you have your positive charge here and you have your negative charge here. So this defines a dipole. And whenever you have a dipole, an instantaneous dipole for given atoms, this will tend to induce some dipoles within the neighboring atoms. For example, now if you have another atoms that is a neighboring atom like this, so if it's a neighbor of the first atoms, because you have this positive charge here, this positive charge is going to attract the electrons of this neighboring atom. So those electrons will be attracted by the positive charge. So they will tend to be more towards the left rather than being towards the right. So it means that they will be concentrated at this point M, while on the other hand, the center, the protons of these atoms will be repulsed, because those are the positive protons within the atom, so they will be repulsed by the positive charge of this neighbor. So in this case, it means that because you have this dipole here, because this atom has an instantaneous dipole, it will induce a dipole to its neighbor, because of the fact that positive charge tends to repulse positive charge and attract positive charge. So now it means that those electrons will be attracted, so they will create an excess of negative charge on the left, and then you will have the rest of the positive charge on the right. So it means that in this case, you will get again a dipole. So you have a dipole that goes between the negative charge to the positive charge. So in this case, it means that you start with, you had an instantaneous dipole, which was just randomly formed by the fact that the atoms are not exactly equally homogeneously distributed around the center of these atoms. This instantaneous atoms is going to induce an atom, is going to induce a dipole within the neighboring atoms. And in turn now, it means that you have now here this induced dipole. But again, if you have this dipole, it means that you have now an excess of negative charge here and an excess of positive charge. Those negative charge are going to attract even further the positive charge here. So again, this now induced dipole is going to induce even further the formation of a dipole in this atom 1. So you started from a case where atom 1 had simply an instantaneous random dipole. This dipole induced a dipole within the neighboring atom number 2, and in turn now this atom number 2 is reinducing again a dipole within number 1, so that overall those atoms are inducing a dipole on each other. So that and this becomes energetically favored, because now it means that you have an excess of negative charge that is interacting with an excess of positive charge. So this is a case where you have two atoms that induce a dipole on each other, and because you have those positive charge that are now interacting preferentially with those negative charge, then you will get a potential energy out of this. And so it means that this is what will govern the cohesion of those atoms. This is because you have those two dipoles interacting with each other, that those two atoms will like to stay close to each other. And this is in this case the van der Waals energy. And this van der Waals energy is very important because in most materials, atoms are neutral. So you have some examples of materials where the atoms are not neutral. For example, ionic crystal, like sodium chloride, for example, like the salt. Then in these types of material, you have some cations interacting with some anions. But in most other materials, the atoms are neutral. So when they are interacting, they are not interacting with Coulombic interaction. because there is no charge. So in that case, they will be only interacting with van der Waals interaction. So the van der Waals interaction is really the main forces, the main energy that is responsible for the cohesion of material. It's responsible for the fact that atoms like to stay attached to each other rather than separated from each other. So this van der Waals interaction is a very important types of energy. And this energy, so this van der Waals energy, if you do the calculation of the dipole interacting with each other, this van der Waals energy is always, so first it's always attractive, so it's always an energy that is negative. You cannot have a repulsive van der Waals energy, it's always attractive. And this energy is always proportional to 1 over R6. So in this case, this is not, this value 6 has a real physical meaning. That's the value that you find when you actually do the calculation of one dipole interacting with another dipole. So in this case, you have an energy that when you plot it as a function of the distance, that's an energy that is negative, always negative, and decreasing as 1 over R6. So it's again an energy that is decreasing to minus infinity when R becomes very small and becoming 0 when R is very large. But in this case, this function decreases towards 0 faster than the function 1 over R that you get for a Coulombic interaction, but more slowly than the function R over 12 that you get for the electronic repulsion. So now if we combine all those forces, all those energies, sorry, that we have seen. So if we take the case of two atoms that are neutral, so they mean that we neglect the Coulombic energy. So in this case, if we summarize what we have seen, if I plot the energy as a function of the distance, so you have two cases. So first you have the repulsive energy. So that's the energy that prevents atoms from overlapping with each other. So this energy, we said that it's always positive. It's a positive energy. It's an energy cost, and it is an energy that we can typically describe as 1 over 1 over R to the power 12. So you have this repulsive energy here that is going very quickly to plus infinity when R becomes close to 0, and then decrease very quickly towards 0 when R becomes very large. So in this case, this is the repulsive potential. It's proportional to 1 over R to the power 12. This is the repulsion due to the fact that the electronic clouds repulse each other. And now, so in this case, if those two atoms are neutral, so there is no Coulombic interaction, but there's going to be the van der Waals interaction. So in this case, the van der Waals interaction is going to be a function that decreases more slowly towards 0, because now it's a function that is proportional to 1 over R6, and in this case it's a negative energy because it's attractive. The van der Waals energy is always attractive. Repulsion energy is always positive. Van der Waals energy is always attractive. The Coulombic energy can be potentially positive or negative depending on whether you have opposite charge or equal charges. So now if we combine those two forces, you have the repulsive force between the two atoms that is proportional to 1 over R12. This energy is going to be dominating at very small distance. At very small distance, this function 1 over R12 increases towards plus infinity much faster than the van der Waals energy decreases towards minus infinity, because it's only decreasing as 1 over R6. So at very small distance, it's the 1 over R12 function that is dominating. Now at a larger distance, it's the function 1 over R6 that is dominating. At large distance, the 1 over R12 function is already very close to 0. It has decreased to 0 very quickly. So now it's the function it's the function 1 over R6 that is dominating at a large distance. And so if you combine those two, so you have a transition where at very small distance, it's the function 1 over R12 that is dominating. And gradually, it becomes the van der Waals function that starts to dominate as the energy is increasing. So altogether, here, if you combine those two things, you get this shape here. So it's a shape, if I replot it on the different plots, it's going to be something that looks like this, where at a very small distance, you have the repulsive energy that is dominating. Then you have an energy minimum that will correspond to the optimal distance between the atoms, for which you have a minimum of potential energy. And then as the distance increases, then the energy becomes close to 0 again. And at some point, if the distance between the atoms is very, very far away, then the atoms do not see each other anymore. And in that case, they have a zero energy of interaction because they do not see each other. So in this case, these types of potential is the most simple potential that you can think of that describe both the repulsion between the atoms and also the attraction. And this potential, this model, is called the Lennard-Jones potential. So in this case, this is the name of this model. It's a model because it's still an approximation of reality. For example, the 1 over R12 repulsive energy, this is an approximation. So it's a simplification of a complex reality. So it's a model. But this model describes pretty well, at least it captures all the physical features. It captures the fact that atoms interact with each other, so they are attracted to each other. And it also captures the fact that, but on the other hand, if the atoms overlap with each other too much, then they will start to repulse each other. So these types of model capture those two things. And so in that case, the typical expression that we use for this Lennard-Jones potential is, so it's a function that depends on the distance, and typically we would write it as follows. So we would write it 4 times epsilon times sigma r to the power 12 minus sigma r to the power 6. And in this case, if you write it like this, so it means that if you look at the point at which this potential is going to reach its maximum, that's going to be obtained for an energy of minus epsilon. So that's the reason we write it like this, with a factor 4 in front of it, so that when you look at the value of this energy at the minimum position of this function, it becomes equal to minus epsilon. So it means that in this case, so you have two parameters here for this potential. You have sigma, which is related to the diameter of the atoms, the typical size of the atoms. And then you have epsilon. Epsilon is going to be the bonding energy. That's the energy that the atoms have, the cohesion energy that the atoms have if they are exactly at the right distance from each other. And then they have a negative energy, an energy of cohesion that is equal to minus epsilon. Now, once you have this Lennard-Jones potential, you can also calculate the associated force. So if you want to go from the energy to the force is going to be equal to minus the gradient of the energy. So the force is always equal to minus the gradient of the energy. And in this case, the energy only depends on the distance. So it means that the force will only depend on the distance as well. And in this case, since the force is minus the gradient of the energy, and the energy only depends on the distance, then the gradient is just the derivative of the energy with respect to the distance r. So if we looked at what this means, it means that if you have an atom here, so in this case, this is an atom for which the derivative of the energy with respect to the distance is negative. So the energy is decreasing with the distance at this point. So the force in that case is going to be positive because the force is minus the derivative of the energy with respect to the distance. So in this case, it means that you will have a positive force that will push the atom to go to larger distance. In this case, I mean, it's because the atoms are too close to each other. They are overlapping with each other. So we'll have a force that pushes them away from each other. On the other hand, now if you take a pair of atoms here at this distance from each other, now the derivative of the energy with respect to the distance is positive. It means that the force will be negative since the force is minus the derivative of the energy. In that case, if the force is negative, it means that it will attract the atom from each other. It will try to force the atoms to become closer to each other. And overall, so if you have an atom that is exactly at the minimum, then because it's at the minimum, then the derivative of the energy would be 0. It means that there would be no force in this case. It means that the atoms are exactly at the right distance from each other. And in this case, they are optimally attached to each other. And in this case, there is no force. So this explains why if you take a materials, if you try to compress this material, you will need to apply a force because you need to force the atoms to partially overlap with each other to become close to each other. In that case, you will need to apply a force because the atoms do not want to overlap with each other. But on the other hand, if you try to take a material and also try to stretch it, to elongate it, you will also need to apply a force because you are forcing the atoms to go further away from each other than what they would like to be. So those forces between the atoms is really what is dictating the mechanical behavior of materials, and this is really what is dictating how they behave if you try to compress them or to stretch them. So now this Lennard-Jones potential, even though it is capturing all the right effect, it's capturing the attraction between the atoms, it's also capturing the repulsion between the atoms. It's the most simple model you can think of that is capturing both the attraction and the repulsion between the atoms. It's made of a simple analytical expression that is easy to compute because it's only 1 over r to the power 12 and 1 over r to the power 6 with no complex function like some logarithm or some exponential that are much more computationally expensive to calculate. But this function it's a model that captures all the right behavior of atoms interacting with each other, but it's typically still very simple. So it can only be applied to very specific materials. And usually it only works well for perfect gases. So perfect gases will typically be well described by these types of Lennard-Jones potential. It can also work to some extent to describe the interaction between atoms, between atoms within the metal. But even for that, it's not a very satisfactory model. So one of the homework that you will have to do at some point is to try to model a metal, some atoms interacting with each other within the metal, and to compare the accuracy that you get when you simulate this using a Lennard-Jones potential or to simulate this using a more complex potential. The Lennard-Jones potential has the advantage of being very simple and very fast to compute, but it's typically not going to offer a very good accuracy. So what we are going to do in a future lecture is to review some more complex models that are more complex than this Lennard-Jones potential that can be used to describe different types of materials. So if you have a material that is, for example, an oxide materials or an ionic materials or covalent materials or metallic materials, those are different families of materials. For different types of materials, you will need to use a different model to describe the interaction of these atoms. And again, like this, Lennard-Jones is one of the most simple model, but it will typically only works well for perfect gases.